All right. Hello. Thank you for being here. Happy Tuesday. An announcement for you. There's a math CS colloquium. Let me pull up um the blurb I've got here. So we've got a mathematical linguist coming to talk tomorrow. Um, which they'll talk about like linguistic structures, and they use algebra to analyze this and get the job done and figure out how we can learn language from a set of data. I think that sounds really cool. I'll be going. They might also talk about like language models, so maybe there's a mention of AI. So we'll see. I think it sounds pretty cool. Yeah, questions? How to do that? Maybe that. I will admit that the information that you have is the information that I have, which is right here. Um, so yeah, um, I'll post this in an announcement maybe later today. Um, but yeah, I think it should be cool. In terms of when and where, so it says knowledge of discrete math will be helpful. So if you've taken that class, great. Um, when and where, it's tomorrow during, what's it called, flex time? 1:30 in 201, which is the big lecture hall upstairs. All right, so that's happening. Just to remind you, your video is due on Friday. Your project you should also be working on. So make sure that you're meeting regularly with your group to get it done. Do not leave any of this to the last minute. Please, I beg of you. Meet regularly, set up a schedule, keep working on it. That way you will run into questions and then I can answer them. Okay. Let me see. I've added the different project things to Canvas. So the module looks a little bit different. So project approval, everybody should have checked off. The next progress report, I'll give you a week because this week's the video. So the next progress report will be next Friday. And to that, oh, I didn't say anything here, but I'm expecting just like a few paragraphs of this is what we did. We met this many times. We have made progress on this, this, and this, and this, and this are what we are going to work on next. So just a quick update so that you feel like you are making progress and communicating it to me. And that way, again, we're not leaving it to the last minute. Okay, so let's pull out the packet and get back to work. So last time we talked about tree reconstruction and chutes and ladders. So I just want to review a little bit. I asked you to think about two questions. One of which is, can we make a tree with only pre and post order traversals? And for chutes and ladders, let's pull that up actually. Okay. So last time we determined that yes, it is possible to reconstruct a tree with pre-order and in order. So my question is if we're given pre and post order traversals. So I don't want to spend a whole lot of time on this. So maybe let's take just 2-3 minutes, discuss it in your groups, see what you came up with, compare notes, and then we'll very briefly talk about it. So turn to your neighbor and talk about it. Can we do this? All right, let's vote by show of hands. of yes, we can, no, we can't, or question mark, we're not sure. Who votes yes, we can? 1, 2, 3, 4, 5. Who votes no, we can't? 1. Who votes not sure? 1, 2, 3, 4, 5, 6, 7, 8. You guys already voted. Okay, so someone who voted yes, maybe not the full algorithm, but why do we think it's possible? Yeah.
That's kind of like my idea was since we already figured out there's already established on can with the pre-order and order conditions. We were to have like an operation of into a post order. I mean the post order into an order of this. Then we're already sending different stuff. And so like for me, like I kind of noticed the bad with it. Or like my idea with the post order is that we identify two subgroups. We identify the subgroups. Is this like a general solution for like having this amount of nodes?
Preferably general, but if you have a specific one.
Yeah, so like my the post order we know that the last node is the pairing node.
Mm-hmm.
So what is the lead that towards the node? Um,
So basically everything but that last one. Okay, that's in post order.
Then you do 6 or 7 total. The first 6, the first 6, and the 7 as the three elements in the list.
Say that again.
You put like basically since and the last one.
Mm-hmm.
It's not with these three.
Okay, so like put it in the middle. So 3, 9, and 5. Okay.
Two subgroups. Which
Mhm. Okay. Yeah, I like the idea of being able to get like we know 10, the first thing in pre-order is the root, which makes the last thing in post-order the root. And then we can kind of stick it in the middle and see like that's probably maybe the subtree split. And we could do that with pre-order too, right? Any other ideas for how we could approach this? Or anyone who said no or not sure, tell me why.
I said no because the pre and the post order give us the root and then the order of the nodes.
Mhm.
And then like tell us how to arrange the nodes, like which one's gonna be a top and which and on the left side or the right side.
Yeah,
I think you like make a tree out of it, but it would be hard to get the exact same.
yeah. Yeah, and I want to push back a little and say like it would be hard, but I think it's possible. So I was doing some Googling. This is actually a lead code problem. if you Google like reconstruct with pre-order and post-order, it shows up as a LeetCode problem, which suggests to me that yes, it is possible. So again, I don't want to, this is more of our reach problem. So if you're doing LeetCode to prepare for interviews, maybe go home and look at some of those solutions and think through, convince yourself how they did it. Okay, so ultimately, yes was right. All right, let's move on to chutes and ladders. Hoping to get to the new questions by the top of the hour. So just a reminder that we're working with chutes and ladders, which is a board with end cells that are kind of folded in on themselves like an accordion. And you roll the dice and you move that number of spaces. And then if you, no, thank you, word. If you reach a ladder, you go to that space. Otherwise, you just land on the space you did. If you land on the space with a chute, then you go back to the appropriate square. And so the question is, A, how do we represent this as a graph? B, how do we know the algorithm, or give me an algorithm to find the minimum number of dice throws to win? Yeah.
Thinking like a minimum spinal tree just for the ladders, so you know what ladders you want to land on and not like skip you. So then you could try and or dice like 6 every time until, or of course missing all the chutes, but because you don't want to take the ladder every time. If the ladder he's gonna skip on other ladders, that's gonna give you even.
Right.
So let's say like make a planning to be first like seeing what ladders you want to land on. And from that, just roll the dice good every single time. But avoid the chutes and the ladders that are not in like the sign. Yeah.
So the thing is that the minimum spanning tree requires weights, and I'm not convinced that weights are required for this solution. I know we talked about like it's possible to have like some positive or negative weights. I'm still not convinced that's the simplest or easiest solution. So the way I think is one of the best two approaches is to first, so what I've assumed is that the vertices are the spaces and the edges are whether one space connects to another. So either it's direct, like 1 goes to 2 goes to 3, or there's a ladder, which it skips ahead, or a chute, which skips back. So now that we've hopefully gotten the graph drawn, the question is, how do we traverse the graph? So if we don't have weights, how do we find that minimum number of dice throws to win? So if we've got a graph like this can be our example, but I would like to know the general case. Okay, take maybe 2-3 minutes to talk about it with your neighbor, get yourself back up to speed, and then we'll chat about it again. Okay, so remember back when we talked about DFS and we said this is one of the applications, topological sorting, which is if we've got a directed acyclic graph, which maybe we don't for this case, because like this is a cyclic graph where we have a cycle, for example, from 2 to 7 and back. So maybe not entirely topological sorting would work, but this same kind of order. And so maybe we apply something like DFS to find the quickest way to get oh yeah, sure, go for it. The quickest way to get from 1 to 10 or 1 to n. Any other thoughts? What are your so in that way, like we still want to minimize something, right? We want to minimize the number of edges that we take. So there, when you said minimum spanning tree, there is still that element of minimality. So maybe we do something like DFS to find min number of edges from 1 to n, and then that prioritizes the ladders. And then once we find that minimum number, then we just, I don't know, mod 6 or something. Take each unit and break it up into the dice roll limit. Maybe this may require a bit more thought. But I think this is like a fairly solid response. Any thoughts on this? Yeah.
So, algorithms, they're like trying to count the game and learn how to play. It's like having multiple routes through the and ladders, like how to have multiple routes over this.
Yeah, and that's the cool thing about graphs is that like we can have one application, but it's like identical to another way of solving this problem. And if we know how to solve that problem, then we can solve this one. That's excuse me, that's like a pinnacle of algorithm design, where if you know how to solve one problem and you can transform this existing into something that you know how to solve, you're good to go. Yeah. Any other thoughts? Yeah.
The issue I was having with that one
Mhm.
is in the case of like really short ladders, like for instance, you roll a 1 and land on a ladder, but it just takes you 2 spaces forward, so it's equivalent to rolling a 4. Then you could have just rolled a 6 and gone past it entirely.
Yeah, and so I think that might be, so yeah, I agree. So ladder I+2 equivalent to I don't know. I don't know how to summarize that, but like the idea where the ladder is too short, I think DFS might be like if we're keeping track of things properly, we may be able to discover that situation. But definitely like if you get this question on an exam where you're trying to design a solution, but you're like, no, that issue wouldn't work, you're running out of time, write that issue down of this is something that I think could work, but this is an issue that I have with it, and it will get you closer to partial credit. Any other ideas that people came up with? Sure.
I wanted to ask, are you able to assign like a weight to an edge? Like, are you able to set that as a variable? Is that something that you can do? Or is it just like a solid number always?
No, yeah, you can absolutely assign data to nodes or to edges. Yeah, especially when you represent it in code of this is the way I'm structuring my graph. So yeah, we can add as much information to the graph as we want or need. Yeah. Other questions, comments? Okay. let's call it a day on Chutes and Ladders. And let's be wedding planners for a moment. So we are planning the seating arrangement for a wedding and we have a guest list. So we've got a list of guest 1, guest 2, guest 3, and so on until guest N. And for each guest, we have a list of people they hate. So guest 1 maybe hates guest 3 and 5, and 7 hates 12, and so on. And we assume that these feelings are reciprocal. So like if guest 1 doesn't like 3 and 5, 3 and 5 also don't like guest 1. And so our goal is to rearrange the seating such that we don't have like 1 and 3 and 5 at the same table. Even if they're like over here, they'll still be able to like glare at each other and make mean faces. So we don't want anyone who doesn't like each other sitting at the same table. So that's what we want. There are only 2 tables at the wedding. So how do we give me an algorithm to find an acceptable seating arrangement? If you know the specific term, maybe tell your teammates, or yeah. We only want 2 tables. If you know the specific term, great. How do we find if a seating arrangement exists? Okay, go for it. Talk with your neighbors. All right, let's check in just for a moment. What's our vertices of the graph? The guests, the people? And what's the edge? The table? So like we've got all the guests and this is table 1, table 2. Yeah. Let's say 2 guests are I and J. I dislikes J means that there's an edge between I and J. I think this is the way to go. So now what's the question? So let's say we have 1, 2, 3, 4, 5, 6, and maybe 1 doesn't like 2 or 3, 3 doesn't like 4 or 5, and 6 doesn't like 4. And then we can draw it as a graph. So like 1 doesn't like 2 or 3, 3 doesn't like 4, and 4 doesn't like 6. If we have a situation where 3 also doesn't like 6, then we have something like this. So now the question is, how do we come up with a solution? So this is the way that our graph looks. Give me an algorithm to find, this is table 1, this is table 2. Talk about it for 2, 3 more minutes. What's our condition for there being no solution? Yeah. Yeah. So So 3 people each dislike each other. So if there's a 3 cycle, which is, that's the three nodes all connected to each other. If that exists in your graph, then no solution is possible. I want to hear your answers before giving you the easy answer. You know the easy answer. Maybe sit tight for a second. Go for it.
Just figure, you know, you make the graph the previous way,
Mhm.
and then you assign them every other. From choose a random, person, and you start assigning, you know, this is table 1. And everyone next to that, that's table 2.
Mhm.
And eventually that'll probably be
Right. So if, yeah, so if, there's an alternating to table 1, table 2. So each person you assign either table 1, alternating 1 and 2. If you reach a point where uh, two adjacent nodes can't be both 1, you can't have both 2. So like table 1, frowny face. Table 1, table 2, smiley face. Okay. Any other? Okay, go for it. Okay.
Build up the graph,
Mhm.
start at a node, any node. Add that instead of find its neighbors and then
Mhm.
adding them to a temporary list as well. Then go through the list and find each node's neighbors, add them to set A. Then just adding them to a template and then just repeat the cycle.
Yeah. So yeah, I would argue that's the same basic structure as this one. Um, um, yeah, and I think this is the easy answer, right? So, just to let you know, there's a specific term in graph theory that we use to talk about this kind of graph. Does anybody know what it is? Yeah. Bipartite. And so bipartite is basically there's the bi part, which means 2, and partite, which means part. That's almost certainly not correct, but you get the idea, right? So the idea is we go back to this graph. Let's say we didn't have an edge between 3 and 6. It won't let me erase it. Okay. No edge between 3 and 6. This means that we are able to find, technically 5 is over here too, because 5 not on bad terms with anybody. But bipartite is defined by having 2 sets of vertices, each of which are independent. So here we've got a set of vertices 1, 4, and 5. They're independent, meaning there's no edges inside this set. So 1 is not adjacent to 4, 4 is not adjacent to 5. 5 is not adjacent to 1. So there's no edges within this set. And similarly, if we disregard the edge between 3 and 6, 2 is not adjacent to 3 or 6, and 3 is not adjacent to either 2 or 6. And because of that, we have a bipartite graph. And so if you knew this term, and this was a question on the exam, then you could say the two tables form a bipartite graph. And one of the things about bipartite graphs is that they can't have odd cycles. So a cycle is where we start at one place and we go around and come back to it. And in a bipartite graph, if you've got an odd cycle, that means that there's an edge within one of your sets. And so, so if there's an odd cycle, so the 3 cycle is an odd cycle. If there was another odd cycle, like a 5 cycle, there would also be no solution. Then this is basically, this is how we solve that if we know the graph theory terms, where if we can divide, or maybe partition is a better word. The solution is found where those are the bipartite sets, which is also what we were doing here, right? So T1 and T2, those are the bipartite sets where we say T1 and T2, these are our two tables, and we'll add vertices as we go, add 1 to table 1, 1 to table 2, and so on, and traversing the edges that way. And that's how we construct our two sets. Questions on that? Cool. All right, so that's wedding planning. Now let's think about the movies. So we are given a set of movies. So movie 1, movie 2, all the way down to movie K. And we've got some customers who want to see 2 movies each this weekend. So each customer wants to see 2 movies. There are only 2 blocks of time where we can schedule it. We can schedule it on Saturday, or we can schedule it on Sunday. And we could also have like movie 1 and movie 3 scheduled at the same time. So we want to divide the time blocks. And we can schedule movies at the same time. And we need to figure out, how do we map the movies to the time slots? So which movies get shown on Saturday, which movies get shown on Sunday, so that every customer gets to see their movies. And so that's the main question. The other question is there a schedule where each movie is shown at most once? And give me an algorithm for that if one exists. So we're working at the movie theater. We want to assign movies to a time so that every customer gets to see both of their movies. Any clarifying questions? Yeah. No, let's say infinite capacity. So that takes care of if like everyone wants to see Avengers Endgame, then maybe that makes our job easy. Other clarifying questions? All right, go for, oh yeah, question?
We know how many, shared showrooms?
I think as many, our theater is as big as we need it to be. Yeah, so many theaters, many capacity. Other clarifying questions? Yeah,
Rating slots or there could be multiple slots.
this is a good question and something that I don't think is clear based on the problem definition. I think maybe based on, movies are shown on Saturday evening and Sunday evening, so maybe it's just like one slot on Saturday, one slot on Sunday. Start there, and if you can't find a solution, then maybe we expand it. Other questions? All right, get going. First question, what's the graph? Work on that first. All right, let's briefly address what's the graph. Anybody? What are the vertices? Yeah.
Honestly, decided to go with, like,
Okay, bipartite graph. So what are each of the sets? And the edges are?
so the third hospital that we have,
So customer I wants to watch movie J and K. Okay. That sounds good to me. Do we want to talk about where we're at, or do we want to keep working on it? Keep working on it? Okay. If this is our formulation, let's think about it. Keep going. All right. Thank you for engaging. Let's okay, so the first idea I heard as I was walking around is essentially what we call like a coloring problem. Which is kind of what we did for the wedding tables, right? So the idea being we have this graph and there's some edges here. And we start somewhere and we label it with something. So like maybe here we label it 1, and then all the adjacent nodes we label 2, and then keep going. And so if we label this 2, then this has to be 1, and then that's 2, this has to be 1, that's 2, this has to be 1, right? So alternating nodes, we label different things. So this is if our vertices are the customers and the movies, and our edges are customer wants to see a movie. We have edge between those. So we could iterate through the graph, color each, not necessarily the customer, because that doesn't make sense to say customer sees something on Saturday or Sunday. We want to label the movies. So option one is to color each movie Saturday or Sunday. And then maybe there's a conflict where a customer wants to see a movie on both Saturday or see two movies that have already been assigned. All right, so that's option one. That doesn't necessarily give us a firm idea of like the answer though. Like we can see the point when we get to a conflict, but I don't know necessarily why that's happening. So something that two other groups did, this is option two. Which is we want to formulate it also as a bipartite graph, where the vertices are just the movies and the edges are let's say two movies adjacent if customer wants to see both. Does that make sense? So if we have a situation where customer one wants to see movie one and movie two, then we would have movie one be adjacent to movie two. So a different formulation of the graph, but still like it's extremely related to if we formulated the graph like this. And you can kind of see that on the board behind me where I tried to have like customers on one side and the movies on the other side. And I walked through the option one to try and say this one Saturday, this one Sunday, and so on. But the way that we proceed with option two is if we iterate through the graph and we do this sort of the same idea as the wedding problem, right? Can assign each movie to either Saturday or Sunday. I would argue maybe without loss of generality, like we could have started with Sunday instead. And we would still run into the scheduling error regardless of if we started with Saturday or if we started with Sunday. So we assign each movie, or we assign a movie to Saturday or Sunday, and then assign its neighbors to, okay, so let's say we assign the first movie to Saturday, and then assign its neighbors to Sunday. And so then we repeat. Alternating. And so in this case, we still want a bipartite graph. So we want a bipartite graph with no odd cycles. And that means that eventually we've gotten to a point where a customer preferences make it impossible. So if we get to an odd cycle, that means there's no solution possible. So here's the prime example of, depending on how we formulate the graph, how we frame the problem, we have the same solution for the wedding problem and the movie problem. That's algorithm design. So we come up with one, great. And then we can figure out how do we apply it to the others. Other options I heard include using like a priority queue. if we want to say like, if the customers rank their preferences from the problem statement. Let's go back to problem statement. I don't see that like a priority is implied. I think it's just, here are the two movies and it's our job to schedule them. Not necessarily customer wants to see this one first, this one second. That would add another layer to the problem. Another formulation is, what if we have more time slots? So like Saturday 1, Saturday 2. And Sunday 1, Sunday 2. Like, what if we have that availability? Does it solve our odd cycle problem? How many time slots do we need before our odd cycle is finished? Do you have an answer for that?
So, like, the other most often, has to be at least as much as the rates the long cycle.
Yeah. Yeah. I think I need to think more about this, because it's possible to have like a 4 cycle, and that's allowable. I think, yeah. Um. Yeah, maybe that plays into it a little bit. A complete graph is one that every edge is present, every edge possible is present. So like for a bipartite graph, let's say we have 2 nodes in each set. That's a bipartite complete graph where every edge possible is present, because that edge and that edge aren't possible. Okay, thank you. So maybe think about these, and then next time we'll talk about the ill-behaved children and the prerequisites, and maybe we'll get to LeetCode. Work on your video, work on your project. Thank you, and I'll see you on Thursday.